Good morning and welcome to AP Statistics. Today I'm going to review really quickly what I went over yesterday for the beginning of Chapter 7, and then move forward a little bit to get a little application involved in what we're talking about. So here's the brief story. Yesterday I said that since not every distribution is necessarily normal, sometimes we try to normalize a distribution with what's called the sampling distribution of the sample statistic. I showed you an example with rolling a die where every outcome, of course, had the same probability of occurrence, 1/6, which was an even or a uniform distribution. We can't use normal probability rules on a non-normal distribution, but then I showed you that if we start sampling, so take 2 rolls at a time, and find the average of the rolls, we might find that the curve begins to normalize. So we found the average of every combination of 2 rolls and saw that it did actually begin to create a normalized curve. And the important thing here was that the center, the average, the middle of that curve, was the exact same center as the original distribution. If you add together 1, 2, 3, 4, 5, and 6, and divide by 6, you find an average of 3.5. When we did the sampling distribution of the sample mean, we saw that the center was still 3.5 because it was the most probable outcome. 6 of the possible averages were 3.5, and then it tapered off to either side symmetrically, which is what causes a normal curve. I also said that if you were to sample in larger sizes than 2, you would find that it becomes more and more normalized, and the only difference between the curve with sample size 2 and the curve with sample size 5 is that the standard deviation becomes smaller and smaller and smaller because the curve narrows and narrows and narrows more and more. So that led us to a discovery about how we can write the standard deviation, as well as the mean, of a sampling distribution of a sample statistic. So for means, or the mean of a curve of sample means, if I take exhaustive sampling within my population and find a sample mean for each sample and graph those sample means, it becomes normalized. But the center of the curve is still the center of the distribution. So the mean of the population is still the mean of my sampling distribution of sample means. The only time it's not is if there's bias in your sampling, if you made a mistake. If there's not a fair distribution, then you're going to find that it's off of the center. But for right now, we're going to presume that it's centered, it was not biased, it's fair sampling. The standard deviation of that same distribution was equal to the standard deviation of the population divided by the square root of its sample size, which is why the sample size made a difference. The larger the sample size is, the larger the denominator is, the smaller the standard deviation of the sampling distribution of the sample mean is. There were some conditions here. We said that we like our sample size to be less than 1/10 of our population. That allows you to use the standard deviation approximation right there. If your sample size is too big, it's too much of your population, you lose all of the variability. It becomes like a little sliver. Peak, down, flat. Doesn't really help us. That's a condition we want to adhere to, and I can't remember right now if they want it to be or equal to, but generally you're never going to get to 1/10 of your population unless you have a very small population. Now, we also want to know that the population is already known to be normally distributed. That always helps, always helps. But in case we don't know that information, we have a little follow-up. So long as our sample is at least 30, we're probably okay to have a normalized curve. All right, now, these are conditions for means. I also said that we could do the same thing with proportions, meaning if we believe that 72% of the population will vote for candidate A, and I take samples of size n throughout the population and find each one's sample proportion for who likes candidate A, and I graph that distribution, I have a sampling distribution of sample proportions, which will, again, normalize the distribution, provided our conditions are met. We also said that the average or center of the sampling distribution of sample proportions is equal to, or should be equal to, the population proportion. Again, provided there's no bias in your sampling methods. We should have the same center as in the population. The standard deviation of that distribution of proportions is a little bit different. It's the square root of p times q, I should have extended that all the way down, over n. So the square root of success, 72%, times failure, 28%, divided by the sample size, whatever my sampling size was. And that's how we find the standard deviation of the sampling distribution of the sample proportion. Similar rules apply here. We want our sample size to be no more than 1/10 of our population. But then we have a little bit of a different condition here. I want to make sure that my NP, the number of people I'm sampling times proportion, so the number of people that say, yes, and also NQ, the number of people who say no, they both have to be at least 10. Okay? That's pretty much the important aspects of what we're talking about here. So, of course, you want to know how it gets used. Okay. Before I tell you how it gets used, I also want to tell you the z-score formulas for what we're about to do. Oops, dropped my clipboard. You know that z-score is equal to typically x minus mu over sigma, right? Well, that's when you're talking about finding the z-score for an individual value. So I'm going to show you an example in a minute, but x minus mu over sigma is fine. But what if I do a sampling distribution and I'm looking for a sample to have a certain mean? The z-score for a sample mean is equal to the sample mean I'm looking for, x bar, over mu, divided by, not sigma because it's a sampling distribution, so it'll be divided by sigma over root n. And similarly, if I want to find a z-score for a sample proportion, it's the sample proportion I'm looking for minus the population proportion divided by the square root of p times q over n. These are the important formulas to use for these concepts. Now, chapter 7 isn't a very long chapter, so I'm going to spend more time on reviewing and examples than I am on new content. This is almost all the content in the chapter, almost. 7.2 focuses on proportions, 7.3 focuses on means. I actually want to start with means, so I'm giving you 7.3's worksheet first. And 7.1 was just the introduction of what we're talking about, which is what I did yesterday. So now that you have the information, and obviously, please write that down because that's a pretty good summary of the stuff you need to know right now. Let's do an example. So I'm going to erase what I got. Obviously, you can always rewind and pause if you want to take those notes. Always a good idea. Here's my example and a comparison of what we're really trying to do. Let's just say that average height is normally distributed. With a mean of, let's say, 66 inches and a standard deviation of 4 inches. All right, so we're not talking about, let's say, men or women, just say average height. I don't really care who we're talking about. 66 inches, 5'6", standard deviation of 4 inches. So within 3 standard deviations, or 1 foot, we'll have the vast majority of all people, which makes sense. Between 4'6" and 6'6" is the vast majority of all adults, let's say. Yes, there are people outside those ranges, which is why there's outliers. But this is just a fair estimate of what we're talking about. Let's continue. I want you to find first the probability of an individual being at least 70 inches tall. Now, we can do this because the population is normally distributed, and I could find the probability using normal CDF. It's not that hard. I'm going to do a little bit of extra math because, after all, on the AP exam, when you have to do something like this, showing some actual computations doesn't hurt. So the only thing we can do is show the computation for z-score. So the z-score for a person who's 70 inches tall is 70 minus 66 over 4. 70 minus 66 is 4, and 4 over 4 is 1. So we're talking about a z-score of 1, a person who is 1 standard deviation taller than the mean or above. So I'm going to use normal CDF from a z-score of 1 to an infinite bound, with 0 and 1 as the mean and standard deviation. And you plug it into your calculator, of course, and you find an answer of 0.1587. There's a 15.87% chance of finding one individual out there who is at least 70 inches tall, 5'10". It's not super tall, it's not super unusual, but that's a person who is 1 standard deviation above the average height. Okay, great. Now, I want you to, instead of finding an individual, find the probability that a group of 5 people chosen at random has an average height of at least 70 inches. Now, this is obviously the key distinction between sampling distributions and just normal probability. I'm not looking for one person right now. I'm looking for a randomly chosen group of 5 people whose average height is at least 70 inches. Now, you should probably think to yourself right away, finding one person who deviates from the norm isn't that hard. But finding a random group of 5 people who on average deviate from the norm is probably going to be harder. You could look around the classroom and you could find one person who is exceptionally tall. But if you looked around the classroom, you probably won't find a group of 4 people whose average height is exceptionally tall. Think about the general population. Can you go into a mall, when malls are actually running, and find a person who is 6'6"? Probably. Malls have thousands of people in them. It shouldn't be that hard. But randomly choosing a table at the mall and finding a group of 5 people sitting there whose average height is 6'6" or taller, it's really unlikely unless the basketball team is having a meal. So, let's find the answer. A group of 5 people. Well, now I'm talking about a sampling distribution because I'm sampling 5 people. We're looking still for a normal probability problem. Number 1, I told you the population was normally distributed. So therefore, my sample size of 5 is okay. If I didn't tell you it was normally distributed, a sample size of 5 would be too small to normalize. We need at least 30. But 5 is fine. I need to find their z-score first, sorry. So let's find the z-score first for that group. The z-score for a group whose average is 70, or let's say higher, is still 70 minus 66. But the standard deviation, that's going to change because I have a group of 5 people. So it's 4 divided by the square root of 5. Remember how the sampling distribution works. The standard deviation is narrowed in inverse relation to the size of the sample. So what do we have here? Well, 4 over radical 5 as my denominator, that's a 1.7889. So you can see that that's, if you just did the calculation, it's 1.7889. It's less than half of what it used to be. So obviously now, smaller standard deviation is smaller area as well. I'm going to get an answer for my z-score of, where is it? Where did I put it? That's the problem with doing things ahead of time. Sometimes you don't see what it is. Okay. I'm going to go get my calculator because I don't want to pause. Let's see. So what is 4 divided by square root of 5? And, okay, so that's a z-score of 2.2361. So the z-score is further out from the previous z-score of 1. It's obviously got less area to its right. And that's why we're going to get a smaller answer. NCDF from 2.2361 to an infinite bound with 0 and 1. What do we get? 2.2361 gets me, what a small answer, 0.0127. Let's pause and consider what that says. There was a 15.87% chance of finding one individual who deviated from the norm by at least 4 inches. But there's only a 1.27% chance of finding a group of 5 individuals who, as an average, deviate from the norm by at least 4 inches. It's much less likely to find a large group who deviates as widely as an individual. Make sense? I hope. It should. Okay. We could do the same thing for proportions, but for right now, I don't really want to. I want to stick to means first. So what I'd like you to do is look at the attached homework, which is 7.3a. Please complete that and submit it to me prior to Monday morning. And of course, if you have any questions or problems, feel free to send me an email or join the meet during period 8, where I will be waiting for you. Hope all is well. Let me know if there's any problems. Have a great day and a great weekend.